Welcome back to Applied Mathematics. In this video, I'm going to be reviewing some properties of addition and subtraction. Certainly, we will look quickly at adding and subtracting exact values, whole numbers, fractions, signed numbers. We'll also look at combining like terms, adding and subtracting algebraic expressions. But we'll spend most of our time looking at adding and subtracting approximate values following the conventions of significant figures. All right, without further ado, let me get my head out of the way so we can dive right into that. All right, starting off with signed numbers. If you're trying to add two numbers with the same sign, say -3 and -5, of course, keep the sign, add them together. 3 plus 5 is 8. They are both negative, so the result comes out as -8. If you're trying to add two numbers and they have different signs, well, in this case, you subtract. 5 minus 3 is 2, and you look at the bigger number, 5 in this case. 5 is positive, so the 2 comes out as positive. But if I swapped the signs between them, well, still different signs, so we subtract, but the bigger number 5 is negative this time, so the 2 comes out negative. The rule for subtraction is simply leave the number on the left alone, change subtraction into addition, take the opposite of the number on the right. The opposite of -5 is +5, and 3 plus 5 is +8. The reason that the rule for subtraction is so important is that it allows us to simplify algebraic expressions. So for example, if I have 2x minus 7 minus 5x plus 9. I have a couple of like terms, right? Terms that have the same variable factor. In this case, the 2x and the 5x both have x. The 7 and the 9 are both constant. If those like terms were together, we could combine them in order to simplify the expression. But because of the subtraction, that's actually a problem. Normally, I don't write this step out, but if you are not entirely comfortable working with subtraction in this way, I encourage you to write things out. There is never a problem with writing too much out. Writing not enough out is where mistakes tend to happen. But change subtraction to addition. +7 turns into -7. +5 turns into -5. Now, because we have just addition, I can rearrange using the commutative and associative properties so that I can get my 2x plus -5x together, and I can get my -7 and 5. How did that 9 turn into a 5? Sorry about that. It was a 9 in the earlier line, and then I wrote it down as a 5 just because I wasn't paying enough attention. This is why talking and writing at the same time is usually frowned upon. But here, piece by piece, 2x plus -5x. Well, 2 and -5 have different signs, so we subtract them. 5 minus 2 is 3. The bigger one is 5. 5 is negative, so this comes out as -3x. And then my constants, -7 plus 9. Different signs, so we subtract them. 9 minus 7 is 2. And the bigger one is positive, so it stays like that. I would say that -3x plus 2 is the correct solution here, but I do want to also mention that sometimes if you're looking at answers in the back of a book or something like that, they might go and take a couple more steps. So rearranging this, we might write it as 2 plus -3x, and then remembering that subtraction is adding the opposite. This is the same thing as 2 minus 3x. There are some people who say that this form looks nicer than the one we came up with in the first place. I tell them that they're thinking too hard about it. But they are both equal. They are equivalent expressions. There is no reason to think that one is better or worse than the other. All right, making a bit more of a mess of things. Here I am subtracting two polynomials. And when you're subtracting two polynomials, it's important to make sure that the subtraction distributes across the three terms. So the first polynomial stays the same. We change subtraction to addition, and we take the opposite of the entire thing in parentheses on the right. So it'll be negative x squared. The opposite of minus 2x is plus 2x, and the opposite of plus 3 is plus negative 3, or if you wanted to write it as minus 3, that's fine too. From here, we can combine our like terms. At this point, I'm going to take some shortcuts. We have x squared minus x squared, which is 0x squared, but 0 times anything is just 0. Adding 0 doesn't change anything, so we can leave that term off entirely. But then we have 2x and another 2x. All told, that's 4x. And then we have minus 5 and another minus 3. They're both negative. So that's going to all told be minus 8. All right, 4x and minus 8 are unlike. They are have different variable factors, so there's nothing else we can do. That's all the further we can take that. One of the nice things about fractions is, well, sure, if you have like fractions, you can add across the numerator. If you have unlike fractions, you can make fractions become like by finding a common denominator. Right? 1/3 plus 1/2. Looks like I can use a common denominator here of 6 to get 5/6 as my result. And that works when you have just numerical fractions. That also works when you have variables involved. So one of the things that will show up every now and then is exact values dealing with circles. So they might have a factor of pi in them. So maybe you have pi over 4 minus pi over 6. Yeah, I know pi is 3.14159, etc., etc., etc. You can put that into a calculator and get an approximate value. But I want an exact value here. So in order to keep this as an exact value, I'm going to treat the pi as a variable and combine some like terms. I can find a common denominator. Common denominator between 4 and 6, probably 12 will be the best choice. So that's going to be 3 pi over 12, and that's going to be 2 pi over 12. Now I can combine like terms. 3 pi minus 2 pi is 1 pi. But 1 times anything is just that thing, so we don't need to write the 1, and we can just write that as pi over 12. All right. I want to bring that example specifically to your attention because problems like this, 1/3 plus 1/2, exact value, give me 5/6. Calculators today can do that. If I type in the fraction 1/3 plus the fraction 1/2 into my calculator, it's going to tell me 5/6. It's not going to try to give me a decimal approximation. If I want pi in my fraction, there's a couple of calculators that can still do that, but they're more rare. Not as many of you are going to have that, so being able to do that by hand is important. And of course, I can throw just variables in, right? That could be x over 4 minus x squared over 6, and then you have everything to deal with the variable expressions, and your calculator becomes less and less useful. All right. I think that's enough on exact values. The last thing I want is approximate values. precision rule says when adding or subtracting approximate values, round the result to match the least precise measurement. To make this make sense, I'm going to go with a silly extreme example. Imagine that I have measured the width of the wall, right? So from one corner to the other corner, the wall in a room came out at 9 feet 2 inches. I measured to the nearest inch because that's all the further that I really care about. After having done that, I have now wallpapered the room. And by putting wallpaper on the walls on the left and right, let's say the thickness of the wallpaper, this is going to be fairly thick wallpaper, right? That's a little bit more than 1/8 of an inch, 0.15 inches. And I could do this calculation if I want to, right? It's going to come out at 9 feet, 1.85 inches. But is that really fair, right? Did the width of the room really change? I mean, yes, in one sense it did, but on the other sense, 1/8 of an inch is the difference between holding the tape measure crooked or not. I measured and I wrote down to the nearest inch because that's all the further I trusted my measurement, trying to measure quickly. And to the nearest inch, you're not noticing the difference that adding wallpaper to the walls is going to cause, even when you're using relatively thick wallpaper like I am here. So I'm going to round this to the nearest whole inch, because nearest whole inch is what I had in the first place. So the width of the room after putting wallpaper on the walls is still 9 feet 2 inches. It hasn't changed, or it has changed, but it hasn't changed enough to matter based on how precise I took the original measurement. All right. That is an extreme, kind of silly example, but I like it because it really emphasizes why the precision rule is what we care about. All right. Think about things a little bit more precise than this. If you are trying to work on a milling machine and you need to mill out a slot in a part that is measured to 0.047 inches, right, to the nearest thousandth of an inch. All right, that's important. That's a high precision. But if you have to machine a part, if you have to machine a cover for that slot, and you go over to the bandsaw and you use a ruler to measure, yeah, that's about 1/20th of an inch, you're losing all of the precision that you gained. So whoever is doing the least precise tooling is controlling the tolerance on everything else. That's the idea that we're trying to establish here. The propagation of error. If you try to be very precise in some parts of your process and you're not very precise in other parts of the process, the errors that accumulate from the not very precise part, where sure, you're trying, you're using your ruler and you're marking things out and you're cutting carefully, but the ruler only gives you so much precision. Because of that, it's going to change the tolerances down the road. It's going to change the tolerances down the road. Normally, the precision rule doesn't come up. The precision rule is something that we tend to kind of smooth over, because usually all of our tooling, all of our work is done to the same precision, in which case, well, all the precisions are the same, you round to the same precision you had before, everything is fine. But when that's not what happens, then you have to think about it, and you have to think about, okay, where is my weakest link? The weakest link is the thing that I have to carry on with. Let me get my head out of the way. I'll do one more example like this. In this case, we are going to try to adhere two parts together, one of which measured 17.475 centimeters, and the other one measured 3.28 centimeters. All right, we can add these. Right, I can just grab my calculator. And 17.475 plus 3.28 comes out at 20.755. But over here, I have a thousandth of a centimeter. Over here, I only have 100th of a centimeter. My weakest link was measuring to the nearest 100th of a centimeter. So I don't want to write down all of the details. I want to round to the nearest 100th of a centimeter. And that's going to give me 20.76 as the correct rounded value for the measurement I just took. All right. I hope that gives you some insight. Again, in theory, these are things that you've seen before. In practice, depending on your pathway to this course, they might be new, they might be unfamiliar, but hopefully now we're on a straighter path to continue onward. That's all I have for you in this video. As always, thank you for joining me. I'll see you next time.